Now that we have a better understanding of how our 555 timer works, let's take a look at how we can configure the external circuitry to make it behave certain ways. So here is sort of a rough representation of our 555 timer. You'll note that around the perimeter of this sort of box in the middle, I have our various pins labeled, the same as we have seen before. And so I've actually also copied down here our block diagram, and so the reason I've included this is going to be useful to reference as we're talking about what's going on with the above circuit. So it might actually be good to have the page open in the notes while we're going through this, but at the very least you can pause the video here and come back to this image as we're discussing. Okay, so what we're looking at first is this monostable multivibrator. And so as we've discussed earlier, what we're going to expect from the output is it's going to have a stable state. For what we've considered here, we're going to have a low stable state. It's going to go high for a prescribed amount of time before turning back to our low state. So this period time that it's high is going to be t, so we're going to work towards figuring out what that is. But more generally, we're going to talk about how this behavior comes about in terms of our understanding of the internal workings of our 555 timer. So in general, what we're talking about for this input pulse over here is we're going to say that this input is usually high, and then we have an occasional low pulse. And so for now, let's just consider an isolated event. Of course, if we wanted to, we could talk about scaling this up to where we have these repeated voltage drops coming in at certain time intervals, but for now let's just say it's one drop and let's consider what is happening here. So this would be sort of our high state up here, and this would be some lower voltage down here. Okay, so let's start by considering this case where our input voltage is high. So let's consider a high voltage. And so I'm going to change the notation a little bit from what's shown in the notes because it's a little bit confusing. But let's consider a high voltage V sub, let's call this V sub 1. And let's say this high voltage V sub 1 is applied to the trigger. And so again, that's going to be pin 2 as shown above with the purple. And let me come up here and annotate this. So this level here would be V sub 1 as I've labeled it down here. Okay, so what we need to do then is we can consider the output of our trigger comparator. So we're going to look at the output of the trigger comparator, which as we'd previously seen was C2. Okay, so I'm going to scroll down briefly, and so we're looking at our trigger comparator here, and we see that our trigger is coming into the negative terminal, and that's being compared to a 1/3 of our VCC on the non-inverting terminal. So again, pause that, look at that as you need, but what we can say then is the output of our comparator, we're going to say it's low, and we can say that because we're going to assume that that V1 is above 1/3 of VCC. So assuming V1 is greater than 1/3 VCC. Okay, so we're saying we have a 0 here on our output, so that means our S is 0 going into our flip-flop there. So let's look as well at our capacitor voltage now, coming back to our external circuitry. So if we assume this is steady state and nothing has sort of happened yet, and we just focus on this upper part here, so we basically just have a DC source and then a resistor and a capacitor in series to ground. If that's left in steady state, this capacitor voltage V sub C is going to charge up to the VCC value. So let's say initially in steady state, that capacitor voltage V sub C is equal to our VCC value, so whatever our power is. And so what that means then is we need to consider our threshold comparator. And so now we're looking at this comparator up here, And so we see the two things being compared are this threshold value, which we're saying is VCC for steady state initially, and it's being compared to 2/3 of our V plus. And so to make this consistent, let me actually change this to VCC. So it's 2/3 of our VCC. And in this case, we're not using that control voltage pin. You'll notice up here I have that connected to ground through that 10 nanofarad, 0.01 microfarad capacitor. So if our capacitor is charged all the way up, then our threshold pin, pin 6, is going to be above the 2/3 of VCC. So threshold pin, which is pin 6, is going to be above 2/3 times VCC. And so what that means, looking at that comparator, is the output of our comparator 1, C1, is high. And so output of comparator 1, we can see, is our R input to our flip-flop. So output of C1 is high, and up here we said output of our trigger comparator is low. So what that means is we have S equals 0, R equals 1. So let's come down here, and we can then say, for this case of S equals 0 and R equals 1, looking at our truth table for our flip-flop, we know that's the reset state, so our Q naught is going to be equal to 1. So again, looking at this block diagram, if our Q naught is equal to 1, we've turned on our discharge transistor. So Q1 is our discharge transistor is on. So now let's come back up to our monostable circuit configuration. So note that our capacitor is also connected to this discharge terminal. So what's happening now is any charge that's stored on that capacitor is going to go into our discharge terminal. So remember, that's here. So basically, what we can do is we can add in, here's our capacitor. And so it's connected to other things as well, but in this case we see it's connected here, and if it has some voltage VC, as soon as this transistor turns on, that current has a path to ground, so our capacitor is going to begin discharging. So coming back up here, when this is on, our capacitor discharges nearly to ground. Okay, so after it has discharges to ground, what we can see is that our VC is going to be approximately 0. We might still have some residual charge based on voltage across our base emitter junction there, but our VC is going to be approximately 0. And so now we can reconsider our threshold comparator. So we're coming back up here and we're reconsidering this threshold comparator on the top, because now our threshold value has changed, because we note that this capacitor voltage is also being input to our threshold. So our threshold value has changed, and it's no longer going to be above that 2/3 VCC we have at our inverting terminal. So let's come down here and write that. So our VCC is about 0, which means that our threshold, which is pin 6, is going to be below 2/3 VCC. And so what that means is that the output of our comparator C1 is low. And so in other words, we can say that corresponds to R equals 0, because remember, output of C1 is our R input to our flip-flop. So again, remember, for our input voltage here in the bottom right, or the bottom left, excuse me, we're assuming that it's staying high, and then at some point, which we've not talked about yet, it's going to drop low. So we're just saying it's staying high right now. And because of that, our trigger comparator will have not changed states. So coming down here, we can say our trigger comparator trigger comparator, which was C2, is still the same, which means our S is equal to 0. So going back to our truth table, we know that our R0 and S0 is just our no change. So what this means is we have no change, and our output is going to stay how it was, which means that it is going to stay at Q0 equals 1. And so previously we had said Q0 equals 1 here, and so it's just going to be staying at that Q0 equals 1. Now, what that means though, coming back to this block diagram, remember we have this inverter here, so if we have a high signal on the left of that, our output is then going to be low. So coming back here, we can then say that this means that our V0 is low, and this is what we call our quiescent state. So this is our stable state. So this is a monostable system. This is the one stable state for this particular oscillator. Okay, so now what we want to do is we want to consider this negative going pulse. So now we're going to say, all right, this input voltage is dropping down to some lower level. So let's see what happens when we do that. So we're going to consider a negative going pulse. And so that's just to say that our voltage is dropping for some set amount of time. And so that's again applied to the trigger input, which as we see above is pin 2. And so let me note again that this is just a momentary thing where we're assuming it goes low and then after a short amount of time comes back high. We'll specify what the requirements are for that amount of time a little later, but it's not staying at that low state. It's going low and then coming back high after amount of time. Okay, so our sort of key point to be watching is when that trigger value drops below 1/3 of VCC. So when, sorry about that, let's clean that up a little. Okay, so when our trigger input drops below 1/3 VCC, because remember that's the value it's being compared to, then the state of that comparator is going to drop, or is going to switch. So then the output of C2 is going to go high. And so let's come up and see what that looks like in our block diagram real quick. So basically we're looking at this comparator again, and we're saying now this value is really low. Once it gets lower than the 1/3 VCC that's seen here, then this output S is going high. So we're going to have S equals 1. So let's come down there and write S equals 1 for this condition. So parentheses S equals 1. But we still have R equals 0 because so far nothing has changed with that. So we still have R equals 0, and so what that means is now, again, we can go back to our truth table. If we have S equals 1, R equals 0, we have our set condition, which means our Q0 is equal to 0. And so what our Q0 equals to 0 does, and so sorry for all the scrolling, but if we look at our Q0 here, if this goes to 0, that's turning our discharge transistor off. So now we are turning our discharge transistor off, which means that our capacitor no longer has a path to ground to discharge. So if it doesn't have a path to discharge, then it's going to begin charging up again. Capacitor is charging up. So we're essentially using this BJT like a switch, which is connecting or disconnecting the capacitor to ground. It's connected to ground when the discharge transistor is on, and disconnected when the discharge transistor is off. Okay, so our capacitor is charging up again. So during this time, our output is high because note that our Q0 is 0, But again, because we have this inverter here, if we have a 0 here, that's going to be a high output. So let's just make a note of our output here. So during this time, our output, which let me just write V naught, is high. And it remains there even if our trigger input goes back high. So even if our trigger pin returns to what we called earlier V1. And so what happens then is we have this S equals 0, R equals 0, which we have already seen before, means we're in our no change state. So that's what happens if we have this pulse come down and then go back up. We're still going to keep this output in a high state. But we know that that's not going to stay like that forever, so let's take a look at when that's going to change. We're going to do that by starting with our capacitor equation during charging. So our capacitor voltage during that charging cycle is given by the following. So we can say our VC of t is equal to the final voltage, so it would eventually charge up to VCC, plus our initial voltage, which we said is approximately 0, minus the final voltage times e to the minus t divided by tau. So of course we can factor out that VCC to clean that up, the VCC to clean that up a little bit. So we have VC of t is equal to VCC times 1 minus e to the minus t over tau, where of course tau is our time constant. And so let's go back up to our original circuit. So again, apologies for all the scrolling. But if we look at our original circuit here, we see that when this is charging, it's charging through RA and C. So our time constant then is just going to be RA times C. So coming back down here, we can say our tau is equal to RA times C. Okay, so it's going to continue charging until it reaches a value above 2/3 VCC. Why 2/3 VCC? Because if we look at comparator 1, our threshold, which is connected to our capacitor, so that's essentially measuring our capacitor voltage, is being compared to 2/3 VCC. So when we pass that, we're going to have our capacitor begin discharging again. So when our VC charges above 2/3 VCC, what we get is our threshold comparator, comparator C1, output goes high. And so as we've seen before, that corresponds to R equals 1. And so we're assuming that the negative going pulse has gone back up to 0, such that our S is 0, and that corresponds to our reset state. So let me write that explicitly. So assuming our threshold, trigger. So we're assuming that our trigger is at the high level of V1, which means our S is 0. So now we have our reset state, which means that our Q naught is equal to 1, which means that our V naught goes low again. And so basically we've returned now to our quiescent state, and our discharge transistor turns on. So this Q naught equals 1 is turning on our discharge transistor. So if we sort of take all of that into account, we said initially our output is low. Then when we pressed our button, so our output was low. We didn't press our button. Our trigger voltage dropped from V1 to some lower value. That caused our output voltage to increase. we let go of the trigger, the button, or in other words, our trigger has increased up to the high value of V1, but even so, this stays here for some amount of time. Once the capacitor reaches 2/3 VCC, it drops back down to 0, or our low level, and it stays at that low level until the next trigger event. So the next thing we want to define then is what is this time t of this pulse. So we can find this using our capacitor charging equation. So what we're going to do is we're going to use this equation, and we're going to say that our time is going to be the time capital T of that pulse, because we know that that pulse is going to sort of go away when our VC is equal to 2/3 of VCC. So plugging in those values to that previous equation, what we have is our VC of T is equal to 2/3 of our supply voltage VCC, and that's equal to VCC times 1 minus e to the negative t, because I'm using capital T for my time, divided by R sub a times c. So we can solve for that, and we see that our period of that pulse t is equal to Ra times c, log of 3, which is approximately 1.1 times Ra times c. So that's the equation that we get for our pulse width. So again, let me point something out here. So this t, which we defined as the width of our output pulse, is only a function of external time constant. So only a function of external time constant tau. And so note, sort of implied in that is that we do not have a dependence on our VCC value. So note here, these two VCCs are canceling out. And so what that tells us is as long as we are in proper range to be powering all of these components inside, so our comparators, our transistor, various things like that, as long as it's high enough to power it and not too high to cause damage, we're going to have this relationship which is independent of that power supply. So kind of cool, very cool stuff here. One other thing to note, we said, let me scroll back up here. So we said in this original circuit, we were assuming that this time that it is low is relatively short, and then it pops back up to V1. So we do want to actually put a restriction on that and say that our triggering input pulse has to be shorter than T. So this duration here has to be shorter than T. So let's come down here and make this note. So our triggering input pulse, so that downward pulse, has to be less than T. So less time or shorter duration than our capital T, because otherwise what we get is we get R and S both equal to 1, and that is our undefined state. So we want to avoid that, and so depending on our configuration, there's different considerations. If we have a pulsed input going to that, we want to make sure that that pulse input is less than our time t. If we have maybe an external triggering system, we want to make sure that the pulse t generated is longer than whatever it is that's causing our triggering event. So that covers our monostable. What we're going to look at in our next video is our astable multivibrator.